Okay, the question is, here's our toolkit graph. Again, 4x4 square here doesn't look like a square. It looks like a rectangle, but it's 4 units high. I've got it a little too high there, but let's pretend that's 4 units high and 4 units wide. And there's our parabola, which looks a little different than it does if we do an actual 4x4 square. It's the same, scale. 4 units here, same as 4 units here. Okay. Well, again, we pointed out in the preceding why we need to do it this way. If we wanted our 4x4 square to have this width and the same height, then 32 would be way up there. That's not the way we want our graph to look. We want our graph to look like this. In order to make this curve fit this curve, it seems like maybe we could take the red dot here and move the whole square. It doesn't look like a square. Over here. Well, let's do that. If we did that, then the square would look like this. I'll throw in this chalk. One end got wet. I did that versus height. Okay, well, that's a little too long. Let's pretend this is the same width as this one. Okay, my 2 units got exaggerated there. If it's done carefully, then toolkit graph will look like this. And it's about twice as high as this graph, assuming this is our actual graph. So, in order to make the toolkit function fit this, we're going to have to squash this thing down a little bit. So if we squash this thing down to something like half its original height, we're going to get a good picture. And then maybe we would have a function that does a good job of modeling our depth. Okay, I'm even going to give you a little preview. If we were to squash this thing down to half of the original height, toolkit squaring function, that's an SQ there, I can't read it. Toolkit squaring function is, we normally say x squared, but since we're using t for time, it's going to be y equals t squared. And there's our toolkit squaring function. If we shift it to the right 8 units, we get y equals quantity t minus 8 squared. Okay. Then walk down to half the height, we get y equals 1/2 of t minus 8 quantity squared. And you know what? I didn't fudge this, but of course, numbers are fairly simple. Turns out that actually, and I had no, I hadn't worked it out previously, that actually, just by dumb luck, happens to match 32 centimeters we get when y equals 0, doesn't it? Or when t equals 0. When t equals 0, y is supposed to be 32 centimeters. Just by dumb luck, if t is 0, then you square -8, that's 64, take half of that, you get 32. Okay, so that actually is our model. That would actually be a model for a cylinder with a hole of the appropriate size, where 32 centimeter depth empties out in 8 seconds. Right there you have it. I'll even give you a little preview in the algebra. If you square t minus 8, you don't get t squared minus 8 squared. You don't get t squared plus 8 squared. You get now, this is something you should know. You should understand the distributive law. There's a strong tendency to want to say it's t squared minus 8 squared when you see that. That's why you do mathematics by rules rather than what it looks like. And of course, you practice the rules so you start accurately seeing what it looks like, and you need to always know what the rules are. We'll talk more about this. Anyhow, this is 1/2 t squared minus 8t plus 32, which is the general form of a quadratic function. An a, like an ax squared plus bx plus c, but in this case, it's an at squared plus bt plus c. A is 1/2, b is -8, c is 32. That should remind you, hopefully, of the quadratic formula, but of course, we'll talk about that and develop that and give you a chance to practice it before we actually expect you to do anything. But there we have it. So, a couple of main points here. First of all, the 4x4 square doesn't usually look like a square. We talked about that previously, why it doesn't, why it's reasonable to put the graph in this shape where the 4x4 square is stored. And then the idea, okay, now we can move this 4x4 square over here. It's about twice as high as it ought to be here. So we squash this down by a factor of 2. And then we have a parabola. It should actually fit this. Should fit the graph, should be able to predict our depth at any given time. Now, we haven't yet learned to draw an accurate parabola, and this one is a great parabola. Okay. It should be, actually, it's not bad, but you can test it. Don't worry about that. So, next thing we want to look at is how do you actually draw these toolkit graphs so that you can do an accurate version of whatever it is you're trying to model. So we'll talk about that next.